Okay, let's get started. My name is Tim Harris, and I'm the session chair for this next set of talks. This is a topic which we saw at the History Day yesterday has been of interest at SOSP throughout the life of the conference. And this is distributed transactions, and it's so popular, it's got 2 sessions in this year's conference. This first one is looking at aspects of distributed transactions in the context of modern hardware. And I'm pleased to introduce our first speaker, Aleksandar from Microsoft Research, who will be talking about recent work on the FARM project.
Thank you. So today I'm going to, as Tim mentioned, talk about the distributed transactions designed to exploit modern data center hardware. And this is joint work with colleagues from Microsoft Research. So as you all know, distributed transactions are a very powerful primitive. They basically provide this abstraction of a single machine that never fails and executes transactions one after another, which makes it basically hide concurrency and failures from distributed systems, so simplifying reasoning and building distributed systems significantly. Despite this, they are not very widely used in systems deployed in today's data centers. And the main reason is, as we've already heard that yesterday, that people believe that transactions are inherently slow. So for this reason, the systems in use today either don't support them at all, or they support some weaker form of transactions. But in this work, we show that there's no need for such compromises by basically building distributed transactions that have strong consistency, so that are strictly serializable, and have good performance and high availability at the same time. To do this, we exploit several hardware trends that are making their way into data centers. The first one is these large amounts of DRAM that we have in machines. So essentially, today, even a commodity server has 256 gigabytes of DRAM, and this is only going to keep increasing because of the Moore's law. We are also seeing this move towards non-volatile memory. And in this paper, we make memory non-volatile using this very cost-effective approach where we keep a battery integrated with the power supply and then use the energy in the battery to flush the contents of DRAM on power failure. And the third trend that we are using are these fast networks with RDMA support. These networks have very high throughput, very low latency, and these are user-level networks that basically bypass the kernel, so they're also very CPU efficient. And if you look at these 3 trends combined, what we can see is that these basically remove the overheads of accessing storage except during the failure case, and they also remove much of the overheads of networking. And this means that essentially the main overheads, bottleneck that remains that needs to be optimized is the CPU. Okay? So you can, as you can imagine, if you take an existing system and run it on this hardware, this is still going to run faster just because we have faster hardware. But in order to fully exploit this hardware, we need to design new protocols that are basically tailored to the characteristics of the hardware. And this is what we do in this work for distributed transactions and recovery protocols. Okay? So as I mentioned, the main goal is basically to optimize the CPU overheads. And while we are designing protocols, we follow these sort of 3 design principles. One is to use one-sided RDMA operations, with the main reason being not only that they give us high throughput and low latency, but also they're very CPU efficient. It is much more CPU efficient to issue one-sided RDMA operation than to exchange messages. The second principle is that we reduce message counts in our protocols. And again, the main reason is that processing messages actually and sending and receiving messaging takes CPU. So an example of this is we designed this transactional protocol that uses 4 phases, unlike traditional 2-phase commit and similar protocols, but is a lot more CPU efficient because it uses fewer messages. And I'll tell you why we think this is a really good trade-off later on. And then also we need to use our CPUs as efficiently as possible. And for this, we basically try to avoid parallelism to use parallelism as much as we can. One example of this is that we allow new transactions to be performed during the recovery of the system, which increases availability significantly. Okay? So in the rest of the talk, I'm basically going to tell you how we use these 3 design principles to build very efficient transactional recovery protocols. Let me first start by providing some background. Basically, we are building this system called FARM, which is our distributed computing platform with the goal of simplifying the task of building distributed systems and exploiting these hardware trends in a simple way. So this is a general platform targeted at applications that have irregular access patterns and that are latency sensitive. For instance, key value stores, graph stores, OLTP databases, and similar. And FARM basically takes a cluster of machines and it stores all data in memory of this cluster of machines. Each machine is going to store data and also execute server and client code. So we have this symmetric model that allows us to exploit locality of access. FARM represents this this memory of the whole cluster as a shared address space, and the applications basically can operate on this shared address space by executing transactions that allocate, deallocate, read and write objects in it. And you can think of these objects as small objects with several tens to hundreds of bytes, so typical object sizes for the applications that we have in mind. Okay? So in the rest of the talk, when I talk about transactions, I'm going to be talking about transactions in this context. So each machine in the FARM cluster contributes most of its memory to the shared address space. The reason is that we basically keep all the data in main memory. And this is done in these chunks of 2 gigabytes in size, which we call regions. And these chunks are exposed for access over RDMA, which lets FARM use RDMA reads to read objects during the normal case operation. This is essentially done by the machine issuing an RDMA read request to the NIC of the machine that holds the data. The NIC is then going to perform a DMA and fetch the data directly from memory and send the response back to the reader without interrupting the CPU. So because we're not interrupting the CPU, this is quite CPU, on the server, this is quite CPU efficient. We also make these reads consistent, even if there are transactions that are updating the data, but I won't have time to talk about exactly how we do this. So for this, you can have a look at our NSDI paper from last year. FARM also uses RDMA writes to implement very efficient messaging. To do this, machines allocate these circular buffers and expose them for access over RDMA. So every sender is going to have a dedicated circular buffer, and to send a message is going to issue an RDMA write request to the NIC, which then again issues a DMA to store data in the circular buffer. Of course, the message has to be processed by the CPU, so the CPU pulls the circular, all the circular buffers and processes the messages as it detects that they have arrived. But note that the sender actually knows when the message has been stored in the memory of a remote machine, even before the CPU processes it, because it gets this hardware level notification from the NIC, and this can be used to optimize the protocols, as I'll mention in a moment. Another thing to note is that the circular buffers are stored in this non-volatile memory, so they're basically persistent. So we use the same scheme to implement transactional logs. Okay? So this is how FARM uses RDMA. Next, I'm going to tell you how we implemented our transactions. So one of the main design goals when designing transactions was to achieve high performance, as this is a perceived downside of distributed transactions. As I already mentioned, we use one-sided operations extensively to optimize the system. We also designed our protocol to reduce message counts as much as possible, again, to reduce the CPU overheads. One of the things that we do, for instance, is we use primary backup replication, which is a lot more CPU efficient or message efficient than if you use the quorum-based system. And it is a good choice in a data center where the latencies vary a lot less than they do in the wide area setting. We also use optimistic concurrency control as much as possible. Again, the reason is that this allows us to avoid locking objects in certain cases, which again results in having to exchange fewer messages and allows us to use these one-sided RDMA operations. And similarly, we do not accesses to reads directly from backups, but only for primaries. This again allows us to avoid locking objects at backups. Okay, so how does the transaction execution work? So as I mentioned, the main primitive in FARM is a distributed transaction. Each transaction is executed by a single thread, which is called a coordinator thread, but at any point in time, we'll have many transactions executed by different threads in the system. And while executing, the transaction can read objects from other machines in the cluster using these one-sided RDMA reads. Transactions are fully general, so transaction can read as many objects as needed to perform the operation. Okay? So writes are also optimistic, which basically means that writes are buffered in the memory, in the local memory of the coordinator until the commit time. And at the commit time, we attempt to commit this optimistic transaction. If the commit succeeds, all the updates are applied atomically to the shared memory, shared distributed memory. Otherwise, the transaction is aborted and typically retried. So how do we commit a transaction? One possibility would be to use a well-known protocol like a two-phase commit. And as you all know, two-phase commit proceeds in this prepare and commit phases. So it requires 2 round trips, basically, to commit a transaction. However, it uses quite a few messages, and it also requires CPU processing on all participants during the transaction commit, even before the commit can be reported. The transaction can be reported committed to the client. So for these reasons, we do not use a two-phase commit, but we use a different protocol. In farm commit protocol, the first step is to acquire logs of the objects in the right set. And this is done by sending messages to the primaries. These messages also contain the state of the new object, so the messages also act as transactional log. The logs are acquired by the primaries by doing local memory accesses. Basically, they try to acquire the logs using a compare and swap, and then send the response back to the coordinator. Okay? The next step is to validate the read set, and validation is done by using one-sided RDMA reads. And validation is basically necessary because we use optimistic reads, and this ensures that validation ensures that the objects haven't changed since the point in time they were read during the transaction execution. Okay, so we need to perform validation because we do not acquire locks on the read set. Not acquiring locks on the read set means that we, for instance, do not spend any CPU on read-only participants in the transaction at all. If the validation succeeds, the next step is to replicate the log, and this is done by the coordinator that writes messages to the backups. And this is done by using these one-sided RDMA writes. There's no need to wait for the backups to actually process the message. When the replication is done, the coordinator is going to update and unlock the objects. And this is done by writing these commit records into the transactional logs of the primaries. Again, this is done using one-sided RDMA writes, and a transaction can be reported committed to the client as soon as the hardware acknowledges the receipt of the messages. Of course, the primary needs to process these messages and apply the updates and unlock the objects. On the backups, we actually apply the objects only at truncation when the transactions are truncated, and this is done in the background, basically. The truncation messages are piggybacked on other messages in the protocol, so this is quite efficient. Okay, so this is how farm commits transactions. And what can we see by looking at this diagram? So first of all, we can see that we use fewer messages than we would in a two-phase commit protocol. But then we also see that we have 4 phases. One thing to note is that we basically use the CPU during the transaction execution only during the log phase on the primaries. So this means that the remaining 3 phases are very low latency because we perform them using one-sided RDMA operations. And this, again, in turn means that the transaction latency is not significantly increased because we have more phases. Okay? So we basically are able to reduce the number of messages without significantly increasing the latency. So this is how farm operates when there are no failures. So what happens when there are failures? Recovery from failures is made more complicated by our use of one-sided operations in the normal case operation. And the intuition behind this is that basically we cannot have the CPU reject messages at certain points of time in the protocol. So typically what similar systems would do, they would receive a request and then would not respond to the request, for instance, if the machine doesn't have the lease anymore. But we cannot do this because the NIC doesn't know about the leases, so the NIC is going to respond anyway. And for this reason, we need to change the way we recover from failures. One way in which we change the recovery protocols is that we need to change the configuration in a different way. We require basically this primitive of precise membership in order to correctly recover in the presence of one-sided RDMA reads. Another thing that we need to do is before we recover transactions, we need to drain the transactional logs. And the reason is that we are using these one-sided RDMA write operations. So some transactions might have been reported to the client as committed, but their logs might not have necessarily been processed. Okay? So While designing our recovery protocol, the main goal was to achieve high availability. So we are using this primary backup replication scheme to reduce the number of messages that we need in the normal case operation. And this means that we will have to reconfigure the system on a failure before we can start processing or continue processing after the failure. So we need to make this downtime as short as possible in order to have the system as highly available as we can. So we do this by using several techniques. So basically, one part of the reason why we have very high availability is that we keep both the primaries and backups of objects in main memory. So all the failed primaries can be replaced almost instantaneously by promoting a backup into a primary, which means that we can start accessing these regions very soon after the failure. In order to recover very quickly from failures, we also need to detect failures very quickly. So we optimized our failure detection quite a bit. And we use 10 millisecond leases, which is a lot shorter than you would use that is used in other systems. This we can do in part because we have a very low latency network, but we also had to engineer the failure detection carefully to achieve this. For instance, we use dedicated network queues to avoid contention at the network. We use dedicated high priority threads in order to avoid contention at the CPU or from the OS, and then we also pre-allocate all memory needed for this to avoid any interference from memory allocation. And the third component to achieving this high availability is actually our use of parallelism. We use parallelism as much as we can to make this downtime short. One thing that we do is we do not sort of hinder parallelism. So we allow operations to keep accessing regions that haven't been impacted by the failure, and we stop processing of the new operations that access the regions have been impacted by the failure for a very short period of time. I'll show you how we do that. And then we also recover transactions in parallel, and we recover data in parallel in order to shorten the recovery time. Okay, so this is our goal and how we basically do it. And so now how does the failure recovery actually work? From a high-level view, it works very similarly to other similar systems. So the first step is to detect a failure, and then we can recover transactions and data. So to detect a failure machine, a single machine on farm has a special role. It's called the configuration manager. The goal of the configuration manager is to detect failures of all the other machines in the cluster. So this machine is going to perform all the application and transactional work as the other machines, but in addition, it also detects failures of other machines in the cluster. To do this, it basically exchanges these heartbeat messages with all the other machines in the cluster. Other machines at the same time detect failures of the configuration manager. So if a configuration manager fails, another machine is going to detect it and take over, and the cluster is going to keep running. Okay? So when a machine fails, this is going to be detected by the configuration manager, and the configuration manager is at that point going to start the configuration change protocol, which is needed because we have this primary backup replication scheme, right? So the first step is to write the new configuration to the agreement service on the side that we use, and in our case, we use Zookeeper. So this is basically vertical access approach. And this agreement service is needed for the machines to agree on the membership of the cluster while they're executing, okay? So how does the configuration change work? As I already mentioned, the first step is to write the configuration at this agreement service, at the Zookeeper. At the same time, the configuration manager is also going to remap regions. So all the regions that have lost some replicas because of the failure now need to be remapped. This remapping is done in a way that improves our availability. As I already mentioned, the backups are promoted to primaries, and so the data is available for accesses on the primaries very soon after the failure. And it also balances the backups that now need to be recreated across the cluster, basically to speed up, to allow recovering data in parallel and speeding up the data re-replication. So after getting the response from the Zookeeper, the configuration manager is going to send this config new message to every other machine that is still in the cluster. And at this point, the machines actually apply the change and stop accessing all the regions that have been impacted by the failure. Okay? Then they send the acknowledgement message to the configuration manager, and once all the config messages are received, the configuration manager then sends a config commit message to everyone else in the cluster. And at this point in time, we can actually start recovering transactions. So the reason we need this three-way message exchange is because we use one-sided RDMA reads. So this basically gives us this precise membership, and the machines, after receiving the config commit message, basically know that everyone else knows about the new configuration, and they have stopped issuing reads to these regions. Okay, so this basically allows us to avoid races between recovering regions and accessing them over one-sided RDMA operations. Okay, so after changing the configuration, the cluster is going to recover all the transactions that need recovering. As I mentioned before actually we recover the regions, we need to drain the transaction logs, meaning we need to process all the messages and transaction logs that haven't been processed before. At this point in time, we also freeze the set of messages that are going to be accepted from the previous configuration. So in case of further failures, we basically are going always to take on the same set of messages from the previous configurations. Okay? So transaction recovery starts after the draining is finished, and it's performed per region. So this 2 GB region of data. Of course, we are going to recover transactions for many different regions in parallel at the same time. And the first step is for the backups to find all the transactions in their logs that need recovering. And then they send these logs to the primaries for these regions. At this point, after receiving all these messages, the primaries are going to reacquire all the logs for these regions. And note that at this point in time, the primary has the copy of the data in main memory because it was an old backup that was promoted to a primary, and also it acquired the logs for all transactions that have been in progress. So the region looks exactly as it did before the failure. So from this point on, we can actually allow accesses to this region. And from this point on, operations on this region are going to be performed in parallel with recovery. So this basically means that we stop accesses to the region for a very short period of time, which lets us have these short downtimes and improves availability significantly. The next step is to replicate the logs. The primary basically writes messages to the backups, and this is needed in order to replicate the logs enough times to tolerate further failures, and then sends the vote to the coordinator of the transaction. New coordinators of transactions are spread around the cluster, and this lets us perform the transaction recovery in parallel, which again further reduces, this contributes to our high availability to the short downtimes that we are going to have. And then the coordinator is going to basically send the decision to all the participants, which are either going to commit or abort transactions. Okay? So this is how Farm recovers transactions. I know this is an involved protocol with lots of steps, but things to keep in mind is that we basically keep the downtime short by promoting backups to primaries and acquiring logs and allowing access as soon as we acquire the logs for the region, and by also performing many of these operations in parallel to reduce the total downtime as much as we can. Besides recovering transactions, Farm also needs to recover data, and in case of Farm, this means re-replicating and recreating backups for the regions that have lost a replica. So this is done in parallel in order to reduce the time needed to replicate the data, similar to some other systems like, for instance, RAM Cloud. The difference to RAM Cloud is that we do not need to wait for the data recovery to complete before we allow new transactions. And for this reason, we do not have to be very aggressive about data recovery or re-replication. So we can afford to pace the data recovery to impact the foreground operations as little as we can. Okay? So this is how Farm recovers from transactions. In the next 2 minutes, I'm going to show you some evaluation results. So we evaluated the system on a cluster with 90 machines. Each of the machines has 2 InfiniBand 56 gigabit NICs and 2 sockets with 32 hardware threads and 256 gigabytes of memory. We use standard OLTP benchmarks, but I'm going to show you only the results for TATP. There are more results in the paper, and we can talk later as well. So first, I'm going to show you the performance results, so the performance in the normal case operation when there are no failures. I'm showing here the throughput latency curve. The x-axis shows millions of operations committed per second, and y-axis shows latency in microseconds. And I'm showing you the median and 99th percentile latency. As you can see, we are able to commit about 140 million transactions per second, so this is the maximum throughput we are seeing. And at that point in the throughput latency curve, the latency is 60 microseconds. Of course, we can halve the latency basically by going to the knee of the curve and by trading off a little bit of throughput for this. So we're able to commit 130 million transactions in 30 microseconds. So the normal case operation performance is quite good. So what happens during recovery? To show you what happens there, we ran the experiment that basically and failed the machine during the execution, measure the throughput over time, and this is a timeline graph that shows what the throughput looks like. So the x-axis shows time going from left to right, and the failure is detected at a point of time 0, and the y-axis shows throughput in millions of operations per second on the machines that survived the failure. As you can see, we are able to recover most of the throughput very quickly after the failure, basically in 50 milliseconds, this particular run, which is sort of the latency that some other systems have for their operations, even when there are no failures. So this downtime is quite short, which gives us very high availability. The next thing I'm showing is basically zooming out the same experiment, and this shows how quickly we can re-replicate data while not impacting the foreground throughput at all. So the x-axis again shows throughput in millions of operations per second, and the y-axis shows how many regions we recover up until a certain point in time. As you can see, we recover basically 84 regions, so we replicate all the failed regions in about 33 seconds. And this is 160 gigabytes of data while not impacting throughput at all. So note these dips that you see in the performance, they happen even regardless of whether we are recovering or not. So these are basically because of high contention periods in TATP benchmark. And only one more graph which shows that we can quickly recover even from coordinated failures. So here we fail 18 machines, basically 20% of the cluster. And as you can see, even in this case, we recover very quickly, in 400 milliseconds. The reason why it takes a bit longer to recover in this case is that we need to recover a lot more transactions. So in this period of time, we recover 130,000 transactions. So this takes 400 milliseconds. Okay? So I'll conclude by saying that I presented farm transactions, which are tailored for characteristics of modern data center hardware. While designing them, we use these three design principles, using RDMA one-sided operations, designing protocols to reduce message counts, and using parallelism as efficiently as possible. We have strong consistency, high performance, and high availability. Thank you.
Hi, Dave Anderson, Carnegie Mellon. I'm going to poke a little. So let me start out by saying I think there's a lot of good stuff in here. Your recovery is awesome. I am a little concerned, though, that you are propagating this myth of one-sided RDMA reads, and you probably predicted that I was going to ask this question. So our work in NSDI last year showed that your graph in figure 2 is actually just drastically wrong and inverted. That if you are willing to invoke the CPU on the other side using the right operations, you can actually get faster performance than using RDMA reads. And then you have available this wonderful processing device to help you implement and design your protocol.
Yes.
So I guess my main question is, what is different in our evaluation setups when we're both doing kind of the same thing that is leading us to these drastically opposite conclusions in successive papers?
Yes, I think the main difference is that essentially we have this symmetric model where we execute both the client and the server code on the same machines, whereas in your paper you're basically optimizing for the performance of the server. So you're basically measuring the throughput of the server.
So I'll give up the mic after this. That's really not true, because when you look at the client CPU requirements in order to implement their part of the symmetric protocol, it's actually higher overall than the sum of the client plus server side. So in your model, what you've done is you've actually shifted burden that's on the CPU, and remembering that every server is also a client, you've shifted the burden over to the client, but it's gone up by a factor of 2. So you're using more aggregate CPU even in the symmetric model.
Yes. I agree that it's possible to optimize the communication protocols further. It might be possible to optimize it further and get to slightly better performance. There are two things. In our experiments, we show that RDMA reads, one-sided RDMA reads, which were implemented slightly differently, are more CPU efficient, and this is the reason why we go for this. Another reason, I think that this is what we are measuring, maybe all of us, is the artifact of the current implementation. So I don't think that one-sided RDMA operations are necessarily inherently more expensive than very efficient messaging. For instance, I don't see a reason why we wouldn't be able to implement one-sided RDMA operations using unreliable datagrams, right? And in this case, I believe that we will get, although we're seeing it even now, that we would get even further CPU overhead benefits, reduction in CPU overhead.
We should sit down and resolve.
We can talk later. Yes. Yes. Thanks for the question.
Atuladia, Google. My question was regarding your validation algorithm.
Okay.
So if T1 acquires a lock on X, and then T2 comes around to validate its read while the lock is ahead,
Yes.
do you fail the validation for T2?
Yes, the validation in that case fails and the transaction is basically aborted, yes.
Okay, great, thanks.
Hello, Malte Schwarzkopf, Cambridge and MIT. Following on from that question, can you say something about the liveness properties of your transactions? Because with the read validation, if you have a high contention on a single object, then presumably you would lose liveness, right? Because you're optimistically concurrent.
Yeah, so live locks are in principle possible, but what we do, we use backoff as you could imagine. So
your clients back off?
Yes, we use randomized backoff to deal with these kinds of situations.
Thank you.
Hi, Peter Desnoyers, Northeastern University. It's great work, but I wanted to probe a bit on your NVRAM assumptions, which aren't well covered in the paper. So do you require the OS, for instance, to be running correctly in order to do that battery backup? How much of the system has to work for NVRAM?
So essentially, the whole system needs to run while flushing the contents of DRAM. But the idea is basically that we integrate a battery that has a lot more capacity actually that is needed than is needed to flush the contents of DRAM to SSD. A nice thing about our approach is this is basically a distributed UPS sort of approach that in the case of a coordinated power failure, that all the machines are going down, even if some of the batteries are possibly not as reliable as we would like to, we still have 3 replicas of data. So we are not relying on a single battery to never lose its capacity.
Okay, so it's safe against certain crashes, but not others.
Yes.